Here's a video answer key for one of the problems we have assigned for quantum mechanics. And what I'll do here is to add audio supplement to the solutions that's already posted on Blackboard. Okay, let's take a look at the problem here. We have the Schrödinger equation. You used eigenfunctions and so on. H psi equals E psi. And if these psi's here are eigenfunctions of the system, then the energies are the eigenvalues or the allowed energies that you can actually measure corresponding to this Hamiltonian. Now what we want to do is to extend this so that instead of just some eigenfunction or a wave function or orbital or whatever you want to call this psi, instead of that being an eigenfunction, suppose that instead you had psi to be a linear combination of these two eigenfunctions. Well, what does that mean? Well, remember in class we talked about eigenfunctions being a basis set. So let's take that and let's see if I can actually do this. Yes, there we go. Let's take that idea and talk about basis sets. So this will be, in the particular case we talked about, there are two eigenstates here, psi 1 and psi 2, and let's say they form an orthonormal basis set. These are the only two values that you could measure. If that's the case, then on one axis will be the psi 1, on the other axis would be psi 2, and any measurement of whatever quantity you want will be along this axis, say A1. This will be the eigenvalue corresponding to this eigenstate, or this will be the values that you could observe corresponding to this particular eigenstate. And similarly, along this axis, the magnitude along this axis will correspond to values you can measure corresponding to the eigenstate 2. Now suppose that we have the wave function as stated in the problem to be a linear combination of these two eigenstates, psi 1 plus C2 psi 2. Now what we want to show is that, well, let's just see in the problem what we want to show. We want to show that the probability of measuring the eigenvalues of this mixed state here corresponds to psi 1, corresponding to the eigenstate psi 1 and psi 2, are given by the square of the coefficients that you're using in this linear combination. So we want to show that the square of C1 is a probability of measuring this particular eigenvalue A1, and the square of C2 is a probability of measuring this particular eigenvalue A2. Now, if we generalize this for a moment, remember when we talked about quantum mechanics and how really nobody really knows what the wave function is, but the standard interpretation is that the square of the wave function is the probability density of finding the particle that corresponds to that wave function in a particular area. So probability density times volume will give you the probability. And we mentioned that was just one possible interpretation of quantum mechanics. And in fact, if you go to the Wikipedia article, here we'll go to the Wikipedia article. There it is, Interpretations of Quantum Mechanics. So there's a whole bunch of different interpretations. And if we go down here, here's a list of them. Some common interpretations. The one that says the square of the wave function is equal to the probability density for corresponding to a particular particle in a particular region of space. That was due to Born. And here we have the Copenhagen interpretation. That is what most people use in terms of interpreting the quantum, what the wave function square means. So the Copenhagen interpretation was, lo and behold, that was developed in Copenhagen and by Niels Bohr and Heisenberg and a bunch of other people. And they talk about electron collapse and so on. So go to Copenhagen interpretation. Here it is, and we have various niches. So what we're doing in the Copenhagen interpretation is that we're going to collapse the wave function on a particular basis set vector. In other words, what we're going to do is, here's the wave function. There is the wave function here, corresponding to some linear combination of psi1 and psi2. And what we're going to do in the Copenhagen interpretation of quantum mechanics is to collapse this wave function along one of these axes here. And when you do the collapse of the wave function, this is what you actually measure. So whether the state of the system is actually here in between these two real measured values, or whether it's something else, the Copenhagen interpretation says that, well, when you make a measurement, you're going to measure one of this, and it doesn't really matter because measurement is what science is all about. Philosophers can talk about what this really means, but when you make a measurement, that's what the physicists and chemists are really interested in. All right, so with that background, let's go ahead and try to figure out what these C1s and C2s mean and associate those with probability. Well, if you check on the online notes to the answer to this problem, all the details have been worked out, but just let's generally start here, and we'll omit details. Suppose you want to measure something, and this quantity, say, will be A, and these brackets mean the expectation value of A. For a system in this state here, this is a capital psi. Well, remember, the expectation value, well, actually, let's use, rather than this bracket notation, let's go ahead and use this integral. Integral over all space, or we're doing it over all space, although you could do it in some subspace, of this total wave function psi star capital psi times the operator corresponding to this observable A times psi integrated over all space, or whatever region you're interested in. Well, you just go ahead and say, okay, we're going to put that up there. And so this will be the integral. We'll do it over all space for now of C1 psi 1. Now this is the lowercase corresponding to the vectors along here, plus C2 psi 2 complex conjugate times the operator times C1 psi 1 plus C2 psi 2. And this is integrated over all space. So there it is. We just substituted in what the state of the system is, and we expanded it in terms of these eigenstates. And let me just go dot, 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 and you can follow the details in online. And what you end up with is the expectation value for that particular observable will just be equal to the coefficient of the first eigenstate times the eigenvalue for that, plus the coefficient for the second eigenstate times the eigenvalue for that. So in other words, we have these two possible eigenvalues, A1 and A2, and what we're saying is that the excitation value will be this coefficient squared times this eigenvalue plus that coefficient squared times that eigenvalue. We now say that if we use a probabilistic determination, what A is, so the value of A will be the probability of finding, or actually measuring, that value of A, P1 times A1, plus the probability of measuring the second value times A2. So this would be the average, the weighted average, where you're going to measure. It'll be the probability of measuring this eigenvalue times the probability of measuring this eigenvalue. If we now do the comparison here, well, it looks like that C1 squared will be associated with the probability of measuring the first eigenvalue, and C2 squared will be associated with the probability of measuring the second eigenvalue. So that means that these coefficients in expansion here are just related to the probability of measuring these eigenvalues. Let's see if we can make more sense of that. We'll again write down our coordinate system here, our space, so-called space. This will be the first eigenfunction. This will be the second eigenfunction. Now suppose we make our state vector here. So this is the state of our system. Again, it's C1 times the first plus C2 times the second. Here we have a lot more of the first eigenvalue in the first eigenfunction than we have in the second eigenfunction. So this means that the coefficient along this axis, C1, is greater than the coefficient along this axis, C2, which means that C1 squared will be greater than C2 squared, which will mean the probability of measuring that first eigenvector or eigenvalue will be greater than the probability of measuring the second eigenvalue. And you can sort of see this because this vector lies closer to this axis here. So you say, okay, looks like we're going to measure the eigenvalue along here greater than, more probable than the eigenvalue along here. Now what I've done here is sort of sloughed off a lot of details and so on, and you have to worry about the fact that these vectors have to be normalized and so on. But in general, I hope you get the idea from a geometric perspective what these coefficients mean when you have a state which is not in any one of these eigenstates. Here's the second problem for this problem set. Get it here. We have consider a 2D, two-dimensional harmonic oscillator. Let's see if we can derive the energies and wave functions for the 2D harmonic oscillator, and then see if there are any degenerate energy levels and what would happen if the spring constant were the same in both dimensions. And we're going to use the same procedure we used in going from the one-dimensional particle in a box to a three-dimensional particle in a box. Our goal is to set up the Schrödinger equation in a coordinate system such that we can separate out variables and then solve the Schrödinger equation separately for each single variable. All right, let's see if we can do that. Well, the Schrödinger equation, again, is just H psi equal E psi. Let's write down the Hamiltonian for a two-dimensional oscillator. The Hamiltonian for a two-dimensional oscillator will be, in the first dimension, say the x dimension, will be minus h bar squared over 2m times the second derivative with respect to x. And we have to use partial derivatives here because we have two independent variables. And then we have the potential energy term, 1/2 kx, where kx is the spring constant in the x direction times x squared. That will be for one dimension. And then for the second dimension, it'll be minus h bar squared, again, over 2m times the derivative, second derivative with respect to the second independent variable here, y, plus the potential energy term in the y direction will be 1/2 ky, where ky is the spring constant in the y dimension times y squared. There's the Hamiltonian. Now, if we take a look at this, we see that this section of the Hamiltonian contains only x numbers, or x variable, and this contains only y. I don't know how to spell only, O-N-L-Y, only y in here. So this suggests that the Hamiltonian is set up in such a way that we can immediately separate out variables. If that's the case, then we can write the wave function to be the product of two wave functions, one that depends only on x and one that depends only on y. So let's sort of get rid of this clumsy notation and just say this is hx. So this is the part of the Hamiltonian that depends only on x, and we'll call this hy as the part of the Hamiltonian that depends only on y. So we can rewrite the Schrödinger equation as hx plus hy. So we separated out x and y, operating on the product of wave functions here, psi of x and psi of y. And again, the total wave function would be the product of the two. Let's see what happens when we actually operate on this. Okay, well, we'll just multiply through here. So this will be the Hamiltonian, which contains only x terms, operating on the product of the wave functions in the x and y directions, plus the Hamiltonian in the y direction, times the product of these two wave functions here. Well, since y doesn't depend on x, here's a derivative with respect to x, but it doesn't depend on y, we can pull out y, so we can rewrite this as the wave function, which depends on y, times hx times the wave function that depends on x, and again, the wave function that depends on x times hy times the wave function that depends on y. Now we note that this is like a mini Schrodinger equation here. We've broken it up, separated out the variables. So h psi, this is equal to E psi, where we're just looking at energies and size and everything on the x. And similarly here, we have h psi, hy, psi y, this should be that. That would be Ey, psi y. So we can rewrite this as, here we'll do the y, psi y times Ex psi x. Okay, so we'll write that as psi, which depends on y, h psi equal E psi, and that's for the x direction. This is Ex times psi x. Similarly, we have psi in the, for the x coordinate times Ey times psi y. And we can rewrite this as psi x depends on x, psi that depends on y, times the sum of the energies Ex plus Ey. And remember that's equal to the hx times plus hy. There's the Hamiltonians for the x and y direction, times we said psi of x, psi of y. Oh look, this is, or let's rewrite it again, h psi, where psi now is a product, is equal to E psi, where is the sum of the energies. Oh, there we go. So we've shown that the Hamiltonian can be separated out into two variables here, x and y, and therefore the wave function, the solution of the Schrodinger equation, the wave function, the wave eigenfunction, will just be the product of independent eigenfunctions, one along the x and one along the y. And that the energies will be the energy separated out from the x plus the energy which has been separated out here on the y. So let's write down what the wave function, total wave function is. Well, that will be the solution to the Schrodinger equation for a harmonic oscillator in the x direction times the solution to the harmonic oscillator in the y direction. These are functions here. So let's just do it. The solution to the Schrodinger equation, harmonic oscillator, x direction, well, that'll be a bunch of constants, remember that, times the Hermite polynomial, associated with quantum number n. This will be for the x direction, e to the minus alpha x squared over 2. So there it is, that's the solution in the x direction, times the solution in the y direction would be the same constants, times the Hermite polynomial, quantum number n, which is a function now of y, e to the minus alpha y squared over 2. So there is the wave function. If you want to know what all the details are, look at the online notes to the answer to this particular problem. And then the energy, we said, was just the sum of the energy in the x direction plus the energy in the y direction. And we know each one of these for the harmonic oscillator in a single direction from our solution there. So this would just be the quantum number. And again, we have to distinguish now between x and y directions. Plus 1/2 times h bar omega in the x, now it's going to be different, plus the quantum number associated with the y direction, plus 1/2 times h bar times omega in the y direction. And what do you mean by omega in the x and y direction? Well, omega in the x direction will be the square root of the force constant in the x direction divided by mass, and omega in the y direction will be the square root of the force constant in the y direction divided by mass. So that was actually quite simple. The key is to realize that the Hamiltonian, and this is Cartesian coordinates, we can separate them out into a Hamiltonian term that depends just on x and depends just on y. That's called separation of variables, which means the solution will be the product of wave functions and the sum of energies, one for each separate direction. So let's go back and see if we answer that question. Yeah, we got the energies and wave functions for the 2D harmonic oscillator. Now, are there any degenerate energy levels? Now, let's take a look at here. Here are Nx and Y. Well, not really. Nx and Ny are independent, and Kx and Ky are independent. So in general, there'll be no degeneracy except perhaps for some accidental degeneracy. Now, let's see if we make the approximation that suppose the spring constants were the same in both directions. Would the degeneracy increase or decrease? Well, let's just see. So if the spring constants are the same in each direction, well, let's go here, that means that Kx and Ky are the same, which means that omega x and omega y are the same, which means these terms here are the same. So really, we now have nx plus 1/2 plus ny plus 1/2 h bar omega. So if the spring constants kx and ky are the same, then you have the energy, total energy, will be nx plus ny plus 1 times omega, where now omega is either this or this. It's the same thing because the spring constants are the same. Now let's see. Forgot an h bar there. Don't forget the h bar. Now let's see if we can have some combinations of nx and ny, which will give us the same energy. And if that is the case, then that's a degeneracy. Well, just as in the notes here, let's do nx and y, and let's do nx plus ny. Well, this could be 2 and 1, that is 3, or this could be 1 and 2, and that is 3. So the energy here will be 4 h bar omega with 2 different combinations of quantum numbers. So this implies that this is degenerate. With different spring constants, we would have no planned degeneracy, although there might be some accidental degeneracy. But when the force constants are the same, then we have degeneracy. So the degeneracy would increase if the force constants were the same.